Okay, for today we're starting with a little penny game because it's introduction to probability. And this penny game has a object of trying to teach you about how to understand probabilities where they're a little more complicated than just flipping a coin. Okay? If I'm rolling 2 dice, do you get that the only numbers I can get from are between 2 and 12? 2 is the smallest I could possibly roll if I'm going to roll 2 dice. Biggest I could possibly roll is 12. All right? So if you spread your numbers out like this, where you have, maybe you have one on the 7, one on the 11, and if you have all 10 pennies that I gave you spread out in such a way that when I roll a 7, you don't get to take off all of the pennies on the 7. You get to take off 1 penny off the 7. If I rolled an 8, see there's 2 pennies on the 8 right now? If I rolled an 8, you'd only get to take off 1 of those 2 pennies. Okay? So the point is, don't just think, oh, I think at some point he's going to roll a 6, so I'll put them all on my 6, and then I'll get to take them all off. No, you're going to take off only 1 for each roll. So when I roll the dice and it comes up a 10, if you happen to have 1 on the 10, you will take it off. So you can basically gamble. Last hour, they should have gambled that 9 was not going to come up very much, but because it only got rolled once out of a whole bunch of rolls. Okay? And yet 4 was like hot. I rolled a lot of 4s. Well, you can't know that ahead of time. So just use the best information that you can to put out all 10 pennies. I'm going to pause for a minute while you put out all 10 pennies on your board. Okay, here we go. First roll is a 6. If you had one on the 6, you would be able to take it off. Not all of them, just the one. Even if you had 6 of them there, you can only take off 1 of them. All right. So now I'm going to kind of do the opposite. I rolled a 6 there, and so therefore I'm going to put 1 on the 6. That's just going to keep track for you of what I rolled a lot of. You know what I mean? By the end, you'll be able to see what actually got rolled. Yes? Okay, so that's a good question. It's like bingo. Okay, sure, you could say bingo, even though this isn't bingo. But I will be asking as we get close, so I can see who's down to like 1 and. Uno. All right. You don't have to say uno. It's not like uno. All right. Try again. Another one. Next one is a 6 again. So if you had 2 on the 6, now you get to take another one off. You're not, of course, replacing them, or the game would never end. Once you take it off, it's off the board, and it stays off the board. All right, next one is a 9. So now I've had 2 6s and 1 9. And then a 4. And then a 5. All right. And the next one. It's a 5. Another 5. Is there anybody that's been able to take one off every single time? Sweet. All right. Here we go. A little further. 5. Did anybody have 3 5s? Nobody had 3 5s. Okay. So, and obviously 5 is hot. There's a 7. A lot of people win on the 7. Okay, who's down to only 2 left or better than that? All right. How many you got left? How many you got left? 2 left. All right, here we go. And this is a 7 lucky 7. Now. And are you down to 1? Okay. And this one's another 7. Now who's down to 2 now? Okay, a couple people down to 2. And a 5. If you had bet big on 5s, would have been good for you on this time. And 5 and 4 makes 9. It's a 9. Who's down to 1 or 2 left? All right. All right, 4 people. 7 lucky 7. Why are there so many 7s? That doesn't seem likely. All right. 6. Who's down to 1? Who's down to only 1? All right. And it's a 4. It's a 12. He called it. Not many times that somebody calls the shot. Babe Ruth became famous for calling his home run, saying, next pitch, I'm going to hit it up there. And then they pitched it, and he hit it up there. It's pretty awesome. He only did it once, and he was right. 6. It seems like there's so... Do you see that there's one of these things is not like the others? I hope you notice that there's one of these things not like the others. Which one is like conspicuously absent? The 8. Okay. Now, is that the way it's probably supposed to go? No. Now, if you think about it, a lot of people go, okay, he has rolled that so many times that the next one has just got to be an 8. Do you see the fallacy of that? Some people think it, though. They really do. They think it hasn't happened for so long, it's just got to happen. Like if I was flipping a coin and I got heads, 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 and then do you get that it's really tempting to think, oh, it's got to be tails next? I mean, it's been waiting so long, it has to be. No, the probability is still the same. So just because they haven't had any 8s doesn't mean we're likely to get one soon. I get how that feels like it should be that way. But that is not how it works. Let me give you a fallacy that there's some, okay, this is a little bit stereotypical, but it's kind of true. Older people in the casinos get superstitious about their slot machines. Have you heard of this before? They've been working this one slot machine, and they've lost like so many quarters. They just keep putting in the quarters, and nowadays it's pushing a button. In the old days, it was pulling a handle. They just keep sitting there and keep doing it. And then they feel like if they just lost like 1,000 times, that their machine is ripe, it's called, or due. Because like I've been feeding this machine so long, it's gotta go off soon. And they will like not go to the bathroom because they won't leave their machine to go to the bathroom because they're just paranoid that they've done all the work of getting that machine down so it's ready to go, and then somebody else is gonna swoop in there, put in 1 quarter, and take their win. And so there was some old people that would actually wear Depends undergarments, which are like basically adult diapers, so that they wouldn't ever have to leave their stool and just keep playing because of that fallacy. So don't get sucked into that. The odds of me getting an 8 next are exactly the same as they were the very first time. Make it fast. Yes? So, but if the claw machine is truly random, then that doesn't mean that every 7th person actually gets to grab the teddy bear or whatever. That's not how that works. Unless the claw machine is purposely done it that way. But that would be kind of dumb. I'm not sure that you're right on that. Because there is some skill involved. You have a 2-year-old walk up with the claw machine, they're not going to be able to put the claw in the right spot. They're just going to clunk it in the corner or whatever. So, anyway. Don't think that that's what's happening at a casino. They don't set it to run every 1,000th time you'll win. That's not how that works. Yes?
My dad's coworker, he does that. He plays the machine.
Plays the slots. Mm-hmm.
And he finally gave up, and then this lady comes to the exact machine, and she played like 4 times, and then she won.
Yep.
She's like, did I win?
Yes.
So mad at
Yep, exactly, because he felt like he had earned it because he had put in all that money and it was his win. That's not how it works. All right. So again, now that I've said all that, I'm probably going to roll an 8. Do you really believe that? Could it happen? Of course it could. All right. And it's a 10. All right. Could have made the same argument for 10. I hadn't thrown any, and look at there it was. All right. That's not how it works. The probability is the same each time. The dice have no memory is a way to say that. All right, here we go. It's another 10. We're getting so close with so many people, this is going to be scary when like I'm going to throw one number, and all of a sudden like 5 people are going to win. All right. It's a 7 lucky 7. It's an 8. Raise your hand if you just won. How many did we just have? Oh, 3 people won. All right. Clear off your boards and start again. You 3 people, come on up forward. Take your choice. All right. Now put your pennies back out there and learn from your mistakes last time. And if all you think to yourself is, well, I better not put 8s out because, you know, like he only rolled 1 8. That's just luck. Now, I will say, if I did this 1,000 times and I kept not getting 8s, I would start suspecting that there was something not random about that. Yes, as in loaded dice. You can actually fix it so that you can't roll a certain thing, or that you can roll a certain thing by weighting the dice. All right, for right now, let's continue. I'm going to just keep going so that you can see, the more I do, the clearer you can see the pattern. All right, this is a 5. Take off a 5 if you had one. 8. Well, see, 8 was due. No such thing. 10. It's a 2. And this is a 6. Now, again, I want to pause for a second to talk about, not actually pausing the video, but how can you get a 2 with a 1 and a 1? That's the only way to get a 2. So there are 36 possible things that can happen when I roll these dice. I know you may not think that. You might think there's only between 2 and 12. No, there's 36 things, because there's one die that has 1 through 6 on it, and there's therefore 6 things for that die. And then there's another die that can roll a 1 through a 6, so there's 6 things for that die. You multiply how many choices you have together, 6 times 6, there are 36 things that can happen when you roll 2 dice. How about the 3? I could roll a 1 on this die and a 2 on that die, or a 2 on this die and a 1 on that die. Because they're 2 separate dice, it matters. 2, 1 and 1, 2 are different. That's because there's 2 different dice. Think of it as like a red die and a blue die or something. All right. You know which one comes up the most? 7. It's not even close. Well, it's kind of close. There is, let's make all the ways we can make a 7. 1 and 6, 2 and 3 and, and then a 4 and then a 5 and then a 6 and. There's 6 ways to make a 7. 6 ways to make a 7. All right, so that's what's critical here, is understanding things like a 3 is twice as likely than a 2. Think about it. This has a 2 in 36 chance, whereas this only has a 1 in 36 rolls that it should happen. Now, actually, 1 and 12 have both come up, and I haven't had 36 rolls. So it's unlikely that that would happen, but it did. It's also unlikely that we'd get no 3s. I haven't rolled a single 3 or an 11. But yet I've rolled things that are less likely than them. Like, if you had picked 3 and 11 and your friend had picked 2 and 12, you'd be like, I'm way more likely to win than them. They've got the 2 and the 12. Those aren't likely. Well, sometimes life happens, and it doesn't come out the way you'd expect. All right, let's roll a few more. As a few more winners here. We got 4. And next we have a 7 lucky 7. 7 is starting to pull away. 6. And 10. 10 has been hotter than it should be. 11 finally rolled. Well, it was due. Ugh, that's not how it works. 10. 3. Finally got a 3. Yeah, well, you knew that had to happen. No, it didn't. There was only a 2 in 36 chance that that would happen right there. Okay, next is another 3. Whoa. That's randomness in action. You just can't control these things. You can expect stuff to happen, but it's random. This is a 4. And a 7. 8. Oh, you got it? All right. With the 8? All right. So you want it on the set. You can come up first, get first pick, and then the people that just got it with the 8, come on forward. And wait, keep your board the same. I'm going to go one more roll, and then see if we get any winners. And if not, we'll go another roll. This is a 10. And one more roll. A 5. Got another person? Who else? Who just won there? All right, 1, 2, 3. No, put your hand down. Who just won there? Raise your hand. Okay, 1. No? Okay. Did you just win there or not? Okay. So the people that just won may come forward and pick out. All right, and I'm going to stop there because I have to have enough for my other classes to win. So, if you didn't win, sorry. This is not a game where everybody gets a trophy. Pausing. So if we're going to figure out the probability you were going to win that game, it would actually be kind of complex. Because if you put your pennies out, listening guys, if you put your pennies out in a really dumb way, then that affects your probability of winning, doesn't it? You know, like there's a kid who says, what was the probability I was going to win? If he had them all on the 2, not good. Like almost no chance of winning. Okay, but if you all distributed your pennies smart, which would not be to put 1 on everything. That's a common strategy. No, not a good idea, because then you have to have a 2 rolled to win the game. And there's only a what chance of that? 1 in 36. Okay, good. So what you probably want to do is spread them out across the middle. 5, 6s, 7s, 8s, and then, I don't know, the people that did win, did you typically have 2 of something or 3 of something on your, like, little stacks? People that just won, raise your hand if you just won. What was the most you had in a stack? 2 or 3 or? Yeah, there's 4 on the 7. Okay, well that makes some sense because it's the most likely one. How about you? 4 on the 7? 3 on the 7? Okay. All right, I think you get the idea. Now that one is about the last half of the assignment. The first half of the assignment is, I think, simpler than that. Because this is kind of counterintuitive. There's a lot of ways to fall into a trap with 2 dice. People think that they're all equally likely. They're not. People think that this is just a little more likely than that, and it's not. It's twice as likely. A 3 is twice as likely as a 2. Same with the 11. It's twice as likely as that is. That just doesn't seem right. And this is the most likely, but it's not like twice as likely as that. It's got 6 ways to win versus 5 ways to win. 5 in 36 chance of this, 6 in 36 chance of that. So 7 is only slightly more likely than 8. And that our numbers worked out really good, except for 8s and 9s were a little messed up. And 10s were a little too lucky. If those 10s had been like 8s and 9s, it would have been just the way it's supposed to be. There's something called the law of large numbers. And that is, if I do this a large number of times, then I will get closer to what it should be. And what it should be is a nice bell-shaped curve where the middle is the most likely and the ends are the least likely. And if I draw it nicer, like this, that is called the normal distribution. And it works for a lot of things, like IQ. A lot of people are in the middle. A lot of people have an IQ that's just a little below normal or just a little above normal. There's not many people who are geniuses. That's out here. And then there's not a lot of people that are educably mentally handicapped, but there are some. All right, so this is a normal distribution. It's same for shoe sizes. There's not many people that have size 17 feet, and there's not many people that have size like 1. Okay, but there's a lot of people that are in that 6, 7, 8, 9 kind of zone for shoe size. All right, let's go to a couple of the words that I need you to know. We already talked about randomness. An event is just as simple as it seems. If I like roll dice or I flip a coin, something happens, then it allows outcomes to happen. And outcomes is when something comes out, when something happens. Guys, stop talking in the back. Thank you. All right, sample space. The sample space is all the things that could happen. Like for instance, with the 2 dice, there's 36 things that could happen. Please unplug. Thank you. The probability. It's the measure of likelihood that the event will occur. The way I want to say it is there's a 0 if there's no chance of it, a 1 if there is a complete for sure chance of it. Flipping a coin, for instance, is a 1/2 or a 0.5, where it could go either way. But I want you to remember probability is what you want over what's possible. And these are wanted outcomes, things you wanted to happen, over possible outcomes, things that could happen. On dice, there are 36 possible outcomes. If you really, really want the 7 to come up, there is 6 wanted outcomes over 36 possible outcomes. So it's wanted over possible. Okay, what you want over what's possible. All right, moving on to this little chart. Already did that one with you. Experimental probability. If I had actually flipped a coin 1,000 times and it came up 3/4 of the times heads and 1/4 of the time tails with 1,000 trials, wouldn't you be suspicious that it was a weighted coin? That is a thing. I'm not saying you can weight one to guarantee that it will come up a certain way, but you can weight dice, you can weight coins, and if you use an experiment to prove, if you do enough trials and it just keeps coming up that way, then even though it's a coin, it doesn't necessarily have to go half and half. And you do an experimental probability where you actually flip that sucker 1,000 times, eventually you can get sure that that coin is weighted or wrong or off. All right. The casinos are very careful about that, because if you bring in your own dice, of course they won't let you use them, but people try to do it all the time. They'll know what color the dice are, and they'll try to like make sure that they match perfectly, and then they'll try to sneak it into the game, their dice, not because they're lucky, but because they've weighted them or they have done something to rig them. So theoretical is what you're going to be doing in this unit. We're not going to actually be doing experiments to figure out the probabilities. We'll just do them theoretically. All right, the classic chart, there's 100 people asked. Of them, we're subdividing it into, there was 87 right-handers and 13 lefties. In this room, for example, how many of you are righties? Raise your hand if you're a righty. Hands down. Raise your hand if you're a lefty. All right, so there's 1, 2, 3, 4, 5 lefties. All right, so there's about 5 out of 30 of those that are lefties. But then they even have more data, like of the lefties, it's 9-to-4 ratio in this class that they had. Now, again, they had 100 people. That's a really big class, but some college classes are that big. So imagine for a moment that you were asked this question. What's the probability you picked out of this class? And if you don't know ahead of time, keep it quiet, please. If you don't know ahead of time, what's the probability you will get a lefty? There are 13 lefties, aren't there? Out of 100. All right, but this is because it was out of 100. What if I hadn't asked the whole class? What if I had just said, hey, lefties, stand up. Okay, lefties, stand up. All my left-handed people, stand up. That's what I actually mean. Okay, now you guys look at this group. If I only pick from the lefties, what's the probability in this room that I would get a girl? 1 out of 5. Even though there's 30 people in this class? Yeah, because we're only picking from the lefties. Thank you. You guys can have a seat again. So, if we're only picking from the lefties, I encourage you to like circle that part of the chart, and then you don't have to even think about this part or this part. When they ask you, if we only pick from lefties, what's the probability we get a male? Well, then we can just use this part and go, oh, so 9 out of 13. If you only pick from lefties, it would be a 9 in 13 chance. All right, moving on. Find this page right here. I'd like you to answer these 3 questions, the top 3 questions. Give an answer as a fraction, and be careful what it's out of. Usually people get the top number right, but a lot of people get the bottom number wrong. Again, it's that lefty thing. What's the probability the person pulled was female? Did you go with 48 out of 100? Raise your hand if you had that one right. Awesome. Now try the other two. They get more complicated. When they said randomly chosen male, could you tell they were only picking from the males? That meant it was narrowed down to just that part. If you used any other number, you screwed up. Get what I'm saying? When they narrow it down to just males, then you can only use that part of the chart, and therefore the answer must have been 43 out of 52. 43 out of 52. Okay, and then the last one, what's the probability the person's left-handed given the person is female? Do you think they have narrowed it down to only being females that we are choosing from? Yes. Said given. When you say given, then the denominator will change. It can't be out of 100 anymore. Watch for that. If they say given, then it can't be out of that, because you're choosing a different possibility, different possible outcomes, and we're only picking females, so we circle this part of the chart. If you use any other number, you screwed up. And then from there, you just answer the question. Left-handed. Okay. 4 out of 48. Raise your hand if you had 4 out of 48. Okay, cool. All right, that's all you needed to learn for today. Let me look at the worksheet with you. We're going to narrow it down to a smaller number of problems, but it's not quite as simple as evens. You may skip all of number 1. That's quite a few questions. Problem 2, I want you to do all the parts of problem 2. We need to do one of these where they have a chart from beginning to end. This should be the easy, happy place of probability. Like, these will be some of your easy problems on the test. Okay, so don't overthink these. The common mistake people make is forgetting that they narrowed it down to only seniors or whatever in the problem. If they narrow it down to only one group, circle that group on the chart and only use those numbers. Okay, number 3, I have to do even though it's an odd one, because it is the classic marbles in a bag problem. This has been done for many years and many times, and it's the kind you're going to see on the ACT test too, and they're not hard at all, really. Okay, I personally think it's awesome to make an actual picture that has it. So 5 green marbles, 1, 2, 3, 4, 5 green ones, 3 blue ones. What if you're having to write 6 yellow marbles and you don't want to use the color yellow? Well, you actually have an iPad, so you could do yellow. But I could write Y for yellow, 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 yellow. There we go. And last 4 white ones. I like to do those as like empty black ones, but you can do it any way you want to. Do you have to do this? No, but I really do think it helps. Now you can see it. If you reached into that bag, what are you most likely to get? Well, what's there the most of? Yellow. Yellow is the one's the most likely. Okay, what's the probability she gets a blue? You reach in. There's only 3 of them in there that are wanted outcomes out of, had anybody added them all up yet? There's 18 of them. So it's 3 out of 18. I am fine with you leaving your answers that way. The answer key is going to give it as a decimal. All you got to do is divide your 2 numbers. But it's a lot faster if you don't have to grab your calculator, so I'm saving you some time here. I think we all know how to put in 3/18 on the calculator, and we'll save the time of doing that. All right, moving on. We did practice the dice thing in class, so you do not have to fill out this whole chart. What you do have to do is this at the bottom, and they gave you one of them. The probability of a 4 is 3 in 36. Do you guys remember what the probability of a 2 was? 1 out of 36. Can you see the pattern developing here? What's coming next? 2 out of 36, then 3 out of 36. And then do you remember what 7 was again? 6 out of 36. There's a pretty easy pattern. If you want to, you can list all the outcomes. Like for an 8, you can use a 1 and, no, that doesn't work. A 2 and 6, 3 and 5, 4 and, see, I think you get the idea. 3 and, oh no, it's going up, sorry. 2, 3, 4, 5 and 3, etc. If you want to list them all, you can, but you don't have to. If you see the pattern, it's pretty easy. Okay, and that's narrowing it down quite a bit. And that's all I have for you for today.